Titan is the only body now in the solar system of any size whose surface we have not seen, and we don't know what's down there. We're very interested to find out. There may be lakes of liquid hydrocarbons. There may be volcanoes spewing methane and other gases into the atmosphere. We just have no idea at this point.
A mission called Cassini is being planned to find out more. But designing experiments to work in an unknown environment after flying 1,000 million kilometers takes time. This program is only a glimpse at the beginning of a very long story.
Well, I suppose it all started in 1989. As soon as the European Space Agency and NASA decided to go ahead with the mission, the Cassini mission, they issued what's called an AO, an Announcement of Opportunity, which is really a call to the worldwide scientific community to become involved with that particular space mission. They say, we're going to launch this spacecraft, this space mission, to achieve these scientific aims. We want people to propose instruments, experiments to fly on the spacecraft to achieve the scientific aims, and you know, it's your opportunity to get involved.
The Cassini-Huygens mission is a vast undertaking. It's a collaborative effort shared between NASA in the US and ESA, the European Space Agency. NASA plans to launch Cassini in 1997. A 7-year journey to Saturn will be followed by a 4-year study of the Saturnian system. The European part of the mission is all contained in a 3-meter diameter probe called Huygens, which will be carried by Cassini. Towards the end of its journey, the mother craft will release Huygens towards Titan. Huygens will plunge into Titan's atmosphere at over 13,000 miles per hour. Over a 3-hour descent, it will slow down so its experiments can measure physical and chemical properties of the satellite's hazy atmosphere. Back on Earth, these measurements will be combined with mapping data from Cassini to build up a detailed picture of Titan. By the time it reaches the surface, Huygens should be falling at only 11 miles per hour. If it survives the impact, experiments will continue to deliver data until Cassini passes over Titan's horizon, breaking contact between Huygens and Earth forever. It was the promise of a few precious minutes on Titan's surface which interested the team of space scientists at Kent.
We submitted a proposal to ESA saying we could build the surface science package, the instrument on Huygens that would attempt to make in situ measurements once the Huygens probe landed on the surface of Titan. And we bid for spacecraft resources. We said we would make this list of measurements. It would cost, in terms of resources, so much mass, so much power, and so much data rate. And that was then considered, along with proposals from other scientific institutes throughout the world. And all of these proposals then go through what's called a peer review process. They are assessed by scientists, by engineers, for their appropriateness scientifically, their technical feasibility, and also from on a practical side, the management capability of the team that we were proposing, because this is a big management task.
The Surface Science Package, or SSP, is only a small part of the overall mission. But the Kent experiments could provide a unique, close-up scientific snapshot of Titan's surface. But how do you design experiments for such an alien world? All Kent have to go on is scant existing data from Earth-based spectroscopy, radar observations, and, perhaps most importantly, data from the Voyager craft, which passed Titan in 1980 and 81.
Voyager took spectacular images of satellite surfaces and all of the major planets in the outer solar system, but Titan was essentially featureless and disappointing from that point of view. However, Voyager had instruments on board that told us quite a bit about the surface, the atmosphere immediately above the surface.
Titan is the only body other than the Earth known to have a nitrogen-based atmosphere. Voyager, however, also detected small but significant amounts of methane. This was puzzling because sunlight should act to convert methane into its heavier relation ethane and other even heavier organic molecules. This process by itself would have destroyed any original atmospheric methane long ago. Many scientists conclude that Titan must feed its atmosphere from some surface supply of methane. This would circulate in the atmosphere, rising to form methane clouds and raining back down with small amounts of newly made ethane. It's possible that Titan now has an ocean consisting of a mixture of ethane and methane ebbing round land covered with solid, heavier organics.
And depending on how much liquid is there, and we really don't know because the theory is uncertain to, factors of 2 or 10 perhaps, the solid materials may in fact be the bulk of the surface. So what we're left with is a very uncertain surface that could be anything from nearly complete liquid to perhaps patches or little lakes of methane. And that makes a surface that is perhaps next to the Earth the most interesting in the solar system, potentially, because of the presence of liquids which go in and out of the atmosphere as water does on the Earth, and because of the potential complexity of having highlands which are dry at the moment and lowlands that are filled with oceans of hydrocarbon.
Kent has selected 7 experiments to make up the surface science package known, because of its shape, as the top hat. Models have been made to show how the package will fit within Huygens. Although computer designs of the top hat look impressive, only raw prototypes of the experiments have so far been built. We're going to look at the development of just 2 of these. The sheer uncertainty facing the team means that Kent has to hedge its bets. A small instrument within the body of the top hat will aim to determine the density of any liquid encountered on Titan. But if there isn't an ocean waiting to catch the probe, a surface penetrometer will measure the shock experienced by sudden impact on a solid surface.
One of the things we really want to answer with the surface science package is what is the actual nature of the surface of Titan? What's it made of? Is it solid like ice, or is it slushy, or is it liquid? And this part of the package, called a penetrometer, this isn't the real thing, this is just a prototype, aims to do that by measuring how hard we land in it as the probe comes down. We measure the impact forces with a force sensor here. And this is just the rig we're using to get the hang of what all the forces mean.
Sand is used in the laboratory to test an experiment which could reveal the nature of Titan's surface in just a fraction of a second. For this crucial information, the scientists of the design team will have waited 7 years. Knowing the nature of Titan's surface might lead scientists to understand more about the processes occurring on Titan. If the surface is fluffy, it can't have been rained on. A sandy or dusty surface might give clues about winds on Titan. A hard, icy surface might imply recent resurfacing events.
We were experimenting with different types of heads. We tried first of all a cone, and that turned out not to be too good actually, although it's the most intuitively obvious shape to use, because the thing just goes sort of straight through without really resisting, and so we can't really measure much of a force. It turns out this sort of spherical shape is better. It gives a much higher force early on. Also, it's more predictable from a ringing point of view. It tends to oscillate a little when you bash it.
Animations show Huygens gently touching down on land. But Kent is all too aware that a really hard surface could smash Huygens apart, bringing the surface science package to a sudden, ignominious end. Less risk is attached to an ocean landing, which many scientists think is more likely. After plunging into Titan's depths, the probe would return to the surface and float. It would be Kent's density sensor which would then come into its own.
It relies completely and solely on there being an ocean there, unlike some other experiments like the penetrometer, which is more operational, if you like, on a tougher surface, or a surface with some granularity or structure to it. This one works through Archimedes' principle, one of the most basic principles you learn at school. And in the arrangement we have here, it's stopped from bobbing to the surface of the liquid by this beam, and so it makes the beam bend. And on the surface of the beam here, we have strain gauges. And when the beam bends, strain is induced in the surface of the beam. And we wire the strain gauges into a Wheatstone bridge, which just compares the resistances of the strain gauges. We amplify the signal from that, and we display the voltage from the bridge here. If I were to change the fluid for something a bit more dense, that's one I prepared earlier, which is, just let it balance out, you see the voltage output goes up. So what we have here is a direct relation between the voltage from the amplifiers to the density of the fluid in which the float is immersed.
Knowing the ocean's density would allow scientists to calculate a relative abundance of methane to ethane. It would be a powerful piece of data. If predictions are right, a slow and irreversible conversion of methane to ethane must be taking place in Titan's atmosphere. That means the relative abundance of ethane in Titan's ocean will gradually increase over time. By knowing its value, an age for Titan's ocean could be determined.
So
but it could be a long way. Well, I mean, it could be 100 meters away or 200 meters away.
and when it is in the cartouche, I call it a cartouche. How do you call this?
The thing which we call
cartouche.
it applicator.
Applicator. Cartouche.
Boring word. Cartouche sounds better. Yeah.
Regular meetings involving key managers, scientists and engineers allow progress to be monitored. The meetings are also an opportunity to discuss changes in deadlines or specifications set by the mission's project managers.
Behind me, there's some 50 scientists and engineers on the mission in their hearing status reports. It's running late, of course, as usual, so our presentation won't be for some time yet. But apart from the main meeting going on, there are also lots of meetings going on in the margins all around us where scientists and engineers are meeting, discussing some of the issues that have arisen in the meeting, horse trading, and so just apart from the main meeting, there's a lot more going on.
In fringe meetings, other concerns are aired. One plan could see launch set back from 1997 to 99. That would miss the chance of a gravity-assisted flight past Jupiter, and in all, a 4-year delay. The different flight path would also expose experiments to much higher doses of radiation, which could cause problems for the sensitive electronics on board.
One has to consider that we may launch in 99. If we do launch in 99, you haven't taken this into consideration. You have failures due to radiation. My God, the recriminations would be awful.
All we've received so far is a memo that says that...
well, that's right, but I mean, this is,
we're asked to,
we're in a dynamic situation.
assess the impact of this change.
Yeah, we can't turn around the EID Part A quick enough to incorporate all this sort of thing. You know, this is pretty new. I mean, you do have this opportunity to respond to the project now with your concerns about this, and that's the proper way to handle it.
Yeah, so we have an allocation of 7.7 kilograms, and 1 kilogram is in the radiation shield that surrounds the detectors. And that was, of course, thinned to the minimum value we thought we could get away with and still meet the requirement. And now the requirement is 5 times higher. That means if you add mass to the shield, you have to add mass to the structural components that hold the shield in place. And at this point in our design, that's a difficult change in our engineering.
And he told me that this will be in the new...
The critical commodities are always mass and power and the cost. And these all have to be traded off against one another in the design of either the orbiter of the probe or in the total spacecraft.
A large project like Cassini, which involves international aspects as well as a good deal of resources in terms of money, in the order of more than $1 billion in just the American part of the venture, requires a great deal of planning, coordination, technical direction at all levels.
One of the problems we have, of course, is putting both of these pieces together, not just physically, but all of the interfaces that we have with 2 pieces of spacecraft, the electrical problems, mechanical, thermal. How are we going to separate the two someday?
Back in the main meeting, John Zarnecki's turn has come to report on Kent's current position, explaining the latest form of the penetrometer.
The force on that probe on impact. Here, a detail of that front end. This is the ceramic piezoelectric force transducer, which will be compressed between these two elements on impact. You might also be able to see, actually, there are two elements, one of which is used for calibration. We're actually able to stimulate the transducer and can use that for a test or calibration. And
Meetings are condensed into 3 hectic days, which leave the Kent team satisfied. New calculations reveal that the danger of increased radiation isn't a problem for the top hat. And they've also negotiated more telemetry time for SSP. Meanwhile, the team back home is having some difficulty getting to grips with a video diary.
There's no makeup, there's no scripts. In fact, all we do is sit down here and start speaking.
We found that if you tap it with a hammer on the top, the longitudinal oscillation like this is at a different frequency than if you tap it on the side and you get this side-to-side oscillation. So by looking at the spectrum of the impact signature, we can determine whether the penetrator landed sort of sideways or vertically.
But that shouldn't be a showstopper. They should be okay for integration in Christmas. Let's just hope that we are.
You ever have one of those weeks where nothing works? Our fax machine is broken, the photocopier didn't work, the coffee machine is broken down, even the BBC's bloody light is stopped, so we have to improvise with this desk lamp.
Anyway, 1993 in Cassini.
Okay, well, 6 months ago we were using this penetrometer design to do the drops in the lab on different materials. But we're now at the stage in the program where in a couple of months we have to deliver the final transducer, much as it will be flown on the spacecraft to RAL. And the final version is rather smaller, as you see. The important thing is to keep the weight down. And we looked at the transducer and how big it needs to be. And it doesn't need to be this big, it's just easy to handle in the lab to make, and it won't break when we drop it on something that's too hard. Whereas for the actual flight, we can make it rather smaller, so that saves a lot of weight. Again, to save weight, we're using here aluminium for this part, and the actual penetrometer head has to be quite hard, so it's actually made of titanium.
Well, we've now mastered the technique of using the moulds for the beam and for the float, and we've now got floats on the end of beams, and we're now putting them into backplates, which are the mechanical interfaces with the wall of the spacecraft and with the experiment itself. Okay. This here is the backplate, which attaches the actual beam to the wall of the spacecraft. These here are the beams on which will be mounted these strain gauges, these strain gauges, and this is the float. This end bit here will be cut off, and the void created will be sealed with epoxy resin.
Time is running out for Kent. Deadlines are allowed to slip, but engineered versions of the experiments still have to be delivered to the Rutherford Appleton Laboratory near Oxford for testing and assembly by the autumn. One last push is needed to complete development.
Last week we donned these crazy suits and went in the clean room to assemble the engineering model penetrator in clean conditions, or cleanish conditions. And here's the result, all bagged up, ready for integration with the rest of SSP.
I too had to don one of those suits that Ralph was in earlier on, and we did a prototype again and an engineering model, which, like all the other bits and pieces, will be integrated into an initial model of all the experiments together, called the engineering model.
We've been doing some electrical tests on the accelerometer subsystem because we had a short circuit just before we wanted to deliver it, so I've been testing it out. One thing that's interesting is it seems the electrical properties change a lot with temperature. The capacitance of this is something like 1/3 at liquid nitrogen temperatures as it is at room temperature.
This is the engineering model. This will be sent away to be shaken, baked and electrically tested in what is called the top hat. That is the thing that holds all the experiments. As you can see, it's quite small and fiddly, but I'm rather pleased with it.
The components of the surface science package have at last reached the Rutherford Appleton laboratory. The density sensor, in a stabilizing plastic shroud, is carefully fitted onto the inside of the top hat's fiberglass shell. The penetrometer, now in its final form, is fixed lower down, in a position where it will become the first man-made object ever to encounter Titan. This version of the top hat is called a structural model. It will be shaken and frozen to test its mechanical reliability. An engineering model will be assembled separately and prepared for electrical tests. Checks continue deep into 1994. If all is well, the experiments will at last be transported to Germany, where Huygens is to be built. The whole probe will finally be sent to NASA's Jet Propulsion Laboratory for integration into Cassini and, hopefully, a 1997 launch. After that, the long wait for 2004 begins in earnest.
One of the particular challenges of a long-term space project like this is continuity of people. Basically, we do not have the financial resources to be able to keep on the whole team during the relatively long period, 6 or 7 years, when Cassini is travelling from Earth to Saturn. So those people will go off. They will do other things. They will find other pastures, most of them. People like myself, who are on the staff here at the university, will keep things ticking over, and we will then almost certainly have new staff involved when we get in 2004, 2005 to the encounter with Saturn and Titan.
There's still the danger of jumping to conclusions in that first cut look at the science data. And in every space mission, it's been the case that much of the understanding has come only years after the data have been returned to the ground, when people have had a chance to analyze the data, when new students, graduate students, and undergraduates have had a chance to take a fresh look and avoid some of the dogmas and prior prejudices of the original investigators. And that was very much true for Voyager. It took 4 or 5 years to really understand what the Voyager data were telling us about the atmosphere and what the limitations were on the surface models based on these data. So I think the same will be true for Huygens and Cassini.
Titan is the only body now in the solar system of any size whose surface we have not seen, and we don't know what's down there. We're very interested to find out. There may be lakes of liquid hydrocarbons. There may be volcanoes spewing methane and other gases into the atmosphere. We just have no idea at this point.